Okay, we will be talking about convolutional neural networks today. That's going to be a build up on top of the last week's lecture. So I hope you basically grasped the content of the last week and you understood the concept of building a neural network. Convolutional neural networks are usually used for image processing. So we will have a very brief image processing course for this week's lecture. And then we will study how we can use convolutional neural networks. So as usual, we will be starting with the summary of the last week, and then we will have a very super quick introduction to image processing. I'm not going into the details. We will just understand the concept of a pixel, how we store an image, the matrix representation of an image. And then we will see something called the convolution operation. And then we will see how we can use convolutional neural networks. Then we will make an example on a database called fashion database, which looks like our MNIST database. So last week we have started the concept of deep learning. We discussed why we need deep learning, and we have seen the more data we can feed into the system, the performance of the deep learning increases. But that was not true for the conventional machine learning or artificial intelligence algorithms. They come to a plateau more quickly than deep learning algorithms. So if you have a lot of labeled data, using a deep learning algorithm for any kind of problem is a much better idea. And we have seen the biological motivation of deep learning or neural networks, and then we have seen how we can convert this biological motivation into mathematical convention. We have seen some definitions, so let's try to remember. Let's first remember why we basically need deep learning. So if we don't use deep learning, if, for example, we use conventional artificial intelligence for image processing, then we need to somehow decide for low-level or high-level features for our problem. And if we decide for this kind of feature, that's called handcrafted features, we may not be able to choose the best feature for our problem. But if we leave this problem to the computer, then it's highly likely that the computer will come up with a much better feature set that we can use. And the neural networks can create a more complex system than what we can handcraft with ourselves. So that was the basic motivation to use deep learning for our problems. And the other motivation was, as we feed the system with data, we can increase the performance of our classifier or learner. That was another motivation for using the deep learning. So people may ask, then why didn't we start using deep learning up until now? So it's becoming much popular nowadays. But when you look at the history of deep learning, that goes back to 50s. Yeah, the stochastic gradient descent, which is the most basic operation for neural networks, that goes back to 50s. But since we had some problems with data, with hardware and software, the popularity of deep learning or neural networks increased after 2012 or 2013. Okay. That was a milestone. 2012 was a milestone basically. And the problems we solved at that time, the first one is big data. In order to use deep learning or neural networks, you really need large data sets, and you need labeled data and access of internet and good connection with internet provided this big data. The second thing is, maybe that's the most important thing, hardware. You really need hardware for neural networks. We will see why we basically need powerful hardware when we start using convolutional neural networks with our example today. That really takes a lot of time if you use a CPU or a low-level GPU. But if you have a good hardware, then things are much better, and you can massively parallelize this kind of architectures. And in order to use this kind of architecture or hardware, you really need a software as well. So you need these three altogether. You need data, you need hardware, and you need software. And now we have a lot of libraries that we can use for neural networks. We usually use TensorFlow for our studies in this lecture, but you can use other libraries. I prefer TensorFlow because it works on Google Colab, which I introduced you in the previous lecture. It's a free service from Google. You can basically execute your neural networks there and get results. And the motivation for deep learning was many neurons connecting to each neuron, and each neuron connects out to many neurons. That's how we create a neural network. And this is basically the biological motivation of a neuron. We said the centroid or the center of the neuron was called soma. The dendrites are the incoming signals, and axon was the outgoing signal. So we have three parts: the incoming signals, the outgoing signal, and the center part, which basically process the incoming signal and decides for the outgoing signal. And that was quite similar in mathematical terms. We have incoming inputs, we have some weights, and we have seen that we have a special weight which is called bias. And the center was basically summing or basically executing these inputs, the input times weight, the input times weight plus, and we had another operation which we called here as the threshold, and by applying this threshold we were getting an output. Okay, and now we have seen by just using this single neuron we can basically solve a lot of logic problems like AND gate or OR gate, but we have seen we cannot basically solve the XOR problem with a single neuron. And when people realized that, they needed to create something called the multilayer perceptron, where you have not just one single neuron, as in this case, but you have a combination of neurons or a couple of layers. Okay, that was called the multilayer perceptron because a single neuron was not enough. And making things a little bit more complicated, you see, we had just inputs, weights, and this thresholding operation in this neuron. But to make it more realistic, we still have the inputs, we have our weights with the inputs, we have a bias term, and instead of applying just a threshold, we have some functions that we called activation functions. And depending on this activation function, the neuron was outputting something as a real value. Okay, so we can take real value inputs, the weights are real values as well, the bias is a real value as well, and by using this activation function we can have a real value output as well. That was basically the mathematical representation of a neuron. Okay, we fire a probability basically with this kind of architecture. And when we look at these activation functions, we had seen three activation functions. We had sigmoid, this is our famous sigmoid function. We have tanh as the activation function, and we have relu as the activation functions. And we have seen we use these activation functions in order to introduce nonlinearity to our network. And in order to use these activation functions in TensorFlow, we had TensorFlow Math Sigmoid, we have tanh, and we have relu in TensorFlow. And as you see on the right side of the slide, if we don't use an activation function, then the decision our network can make is a linear decision. And we know that we cannot solve a lot of problems with linear decisions, so we need much more complex decision making, and the activation function is basically used in order to introduce nonlinearity and we can make much more complex decisions. And we have seen how we can basically train our neural network. We knew the concept of gradient descent or stochastic gradient descent. We start from somewhere, a random point, we go in the opposite direction of the gradient. So we go down the hill. So we are trying to minimize stuff, right? And the algorithm was called the gradient descent. And since we have a lot of variables, we have our weights, we have our biases, and we have thousands of them. So we need an algorithm called backpropagation in order to calculate these weights and biases. And that was using chain rule from calculus. So just to summarize, we have seen the concept of perceptron. These are the building blocks of neural networks. We have seen the activation functions. We have seen how we can create a neural network. We had seen the concept of layer that we will be using a lot today. So these are the layers, and these are the neurons in the layer. And we have seen how we can basically train these neural networks. Then we made a very simple example where we had just one neuron. Okay, we try to solve the problem of converting Celsius to Fahrenheit. You can think this as a linear regression problem, basically. You have one variable, one independent variable, and we are trying to solve the problem of finding a line, y is equal to a times x plus b. And if you remember from the high school physics lecture, this is basically the formula to convert Celsius to Fahrenheit. This is the equation of a line. This is a times x, this is x, plus b. Okay, this is the formula we are trying to solve. We are trying to get a and b. And we used a single neuron for that. And let's go through the TensorFlow code so that we can remember what we basically did. The initial thing was to create a sequential model with TensorFlow. That's how we did this. We said TensorFlow.keras.sequential. That's creating the sequential model. And then we basically added the layers. We added a dense layer here. We added a dense layer where we have one neuron. This unit was defining the number of neurons. And for the initial dense layer, we had to tell TensorFlow how many input variables we will be having in that layer. And since we will be just feeding one variable, we said input shape is 1. Okay, and this is basically our one neuron ultra simplistic neural network that will be solving the Celsius to Fahrenheit conversion problem. And in order to get information about the model, the neural network we created, we were using the summary commands from TensorFlow, and it was basically giving the shape of each layer and the number of parameters in that layer. And if you look at this very simple neural network, we have one layer, okay, and the output shape is basically 1. It's having just one input and outputting one output, and it has two parameters because we have one weight, as you see in this picture, and we have one bias. Okay, input times the weight plus the bias goes into the activation function, and it outputs or it fires a value. And here comes a little bit more complicated part of creating the neural network. We were defining an optimizer as well as a loss function, right? Because if you remember from two previous slides, we were trying to solve a minimization problem. And in order to solve this minimization problem, we need to define what we would like to minimize. That's basically the loss function. And we need to tell TensorFlow which optimizer it needs to use. There are a couple of optimizers for regression and classification problems separately. And you need to tell TensorFlow which optimizer it needs to use. And in this case, we will be using Adam optimizer and loss function as mean squared error. And after defining our model, this was basically the definition phase of our network creation, the command we will be using is, again, it's model.fit. Okay. And here we just have another thing where we define the number of epochs. That's basically the same with all the other models that we used up until now. We give the train set, X train set, we give the results for the train set, and we define the number of epochs. So this is basically how we create a one neuron, ultra simple, very basic neural network. Okay. And let's try to revisit the previous quiz. A neuron is composed of the biological neuron, the dendroid, soma, axon. That's all three is basically creating one neuron. The simple perceptron can solve XOR problem. It cannot unit multi-layer perceptron. That was an important definition. Which of the following operators genetic algorithms rely on? That's a question from the previous lecture. That's mutation, selection, and crossover. That's basically all of them. Which of the following is true for genetic algorithms? The one most responsive to change survives. Multi-layer perceptron can solve XOR problem. That's true. Please try to remember these two questions. Why deep learning is popular nowadays? That's computing power, open source tools, better access to labeled data. That's basically all of them. By crossing over these two genes, which DNA we cannot get? That's basically this one. Which of the following is not an activation function? We have seen ReLU, TAN-H, and sigmoid are activation function. So the inverse is something so else. We use activation functions to introduce nonlinearity networks. That's true. ReLU is usually used with hidden layers. That's true as well. Okay, now we are done with the previous lecture. We will be starting with a super quick introduction to image processing. As I said, we will be using convolutional neural networks for image processing tasks such as object recognition or object classification. So you need to know a little bit about image processing in order to understand this problem. So what we will be doing today, we are going to create a network. So this is going to be the network we will be creating. Okay. And these are all the convolutional layers. Don't worry about that. You will understand all of them, what they will be used for. And the problem we will be solving is we will try to classify images. So we will input an image. For example, we will input this image and we will classify whether this is a dog, cat, lion, or a bird. Okay, that's a classification problem. So what we will be doing today is we will be trying to solve the image classification problem by using convolutional neural networks. And in order to do that, we need a little bit basic image processing knowledge. We need to understand the concept of convolution, and we need a little bit understanding of neural networks. Okay, so we have seen a little bit image processing up until now. You need to understand a little bit about neural networks. You don't know the concept of convolution yet. We will be seeing what convolution means. And at the end of this lecture, you will be able to solve basic classification problems, and you will be able to understand most of artificial neural network architectures by yourself. Okay, so what's an image? This is an image, okay? And an image is composed of pixels. Each square block on the image to the left are called pixels. These guys are called pixels, okay? This is as small as an image gets. You cannot get any smaller than these pixels. And you see, this is one pixel. that's basically black. This is 1 pixel, that's basically red. And these are pixels. These two guys are pixels that are white. Okay, and this is a discrete architecture. An image is basically a matrix. What do I mean that? For example, if you remember this slide from our MNIST database, our MNIST images were images of 28 pixels. You see, 28 pixels by 28 pixels. I mean, we have 28 pixels for the columns and we have 28 rows. And each of these pixels are represented as a brightness value. So basically 0 means it's dark. 255 means it's as bright as it gets. And the values in between, if you are closer to 255, that's closer to white. And if you are closer to 0, that's closer to black. So that's basically all you need to know about the representation of an image. An image is represented as a two-dimensional matrix, and each element of this matrix are called brightness values. So these two things are the only things you need to know about image processing in order to understand today's lecture. So we have this concept of digitization when we talk about image processing. So this is a real image. But in order to represent this real image as a matrix, you need to discretize it. Okay? And when you discretize it, you will be given a number of columns and rows. For example, in this case, this is a very detailed image, right? But you are given certain number of columns and rows. So you need to discretize this image as something like this. Okay, this is called discretization or digitization. And this is a very high resolution image because you need a lot of pixels to represent this image. But you need very few pixels in order to represent this image. Okay, the resolution is one thing we will need to understand in order to understand the concept of convolutional neural networks. Because what we will be doing with CNNs is we will basically reduce the dimension of the image as well. So we will create low resolution images with CNNs. So let's try to understand the concept of pixel. That's the ear of the animal, and that's 1 pixel. As I said, you cannot go any smaller than this. Okay, this is 1 pixel. And as you see, the image is discrete. It's not a continuous function because you can see the boundaries. Okay. So what is the definition of image processing? It's basically a combination of algorithms that alter an input image to create a new image. Okay. It's a set of algorithms that alters the image to create a new image. So input is an image and the output is also an image. As you see in this example, that's the original image. We apply an image processing algorithm, which is a Sobol filter in this case, and we come up with something like this. Okay. Or we can basically use image processing for noise removal as well. So we have a tomography image or an X-ray image which doesn't give a lot of information as the original image, but if you apply some filters, then you come up with a much better looking image, which is the same here. There is a lot of noise, so these little salt and pepper guys are called noise. Okay, and if you apply the correct filter, you can basically get rid of this noise. Or in this case, you have problems with the contrast of the image, and in order to make it much better looking, you can change the contrast of the original image in order to get this one. So all these operations, they are image processing operations. adjusting the contrast, removing the noise, making it look much better. These are all image processing operations. So you can basically adjust the contrast of an image with image processing as well. This is the original image. If you reduce the contrast of the image, you come up with something like this. If you increase the contrast of the image, you come up with something like this. Okay. And we have this concept of edge detection. I think that's clear by the definition or by the name of the operation. You have edges in the pixel. So you have borders in the image, and the aim of this operation is to detect these edges. So these are basically the edges. The white guys are basically the edges you can detect with certain filters when you apply image processing. And the representation of the image, we said that's a two-dimensional array with m columns and n rows. And in order to represent a single pixel, what we usually do is we use the abbreviation I, that's the abbreviation of image. IUV means that's column U, row V. Okay, that's the single pixel of this image, which is an n by n matrix, and IUV is the column U, row V. Okay, and this value will be something between 0 and 255, if that's a gray level image. And there is this concept of RGB or colored image. Don't get confused with that. Just for now, just think an image is a grayscale image, black and white image, and each pixel is represented with one brightness value. Okay, let's not make things complicated. So we need to understand this spatial resolution concept. We have seen the resolution basically affects stuff. Okay, so this is a high resolution image. And as we reduce the resolution of the image, we come up with something like this, which still looks like a rose. This is a rose. This still looks like a rose, but this image has a much lower resolution than this one. It's similar here. This image, which still looks like a rose, it has a much more lower resolution than this image. Okay, so this is the concept of spatial resolution. So that was basically what you needed for image processing. You just need to remember an image is a two-dimensional array. Okay, and each pixel is represented by a value which is called a brightness value. Just know these two things, and by applying some operations on this image, you can come up with a different image, and this is called image processing. Okay, these are just the things you need to remember in order to understand the CNNs. Okay, so what do we do with convolutional neural networks? We said an image is just a matrix of numbers that's represented by brightness values. So this is the image of Abraham Lincoln, and this is basically the brightness values we use to represent the person. Okay, so this is what we see. This is what the computers see, a two-dimensional matrix. And the problem we are trying to solve is we represent our image as a two-dimensional matrix, and we apply a classification algorithm in order to get the probabilities of this image being Lincoln, Washington, Jefferson, or Obama. Okay, that's the problem we are trying to solve. At the end, our convolutional neural network will give a probability for each possible class. Okay, it's not just gonna say this guy is, for example, Obama. It's going to just give a probability of this guy being Obama or being Washington. Okay. How do we do that? Basically, we have two methods. We can either use classical or conventional machine learning algorithms. And in order to classify something, for example, Let's say we would like to classify this image as a face. So what would you do? You try to find noses, you try to find eyes and the mouth, right? And in order to say this is a vehicle, you would like to find the wheels. You may try to find the license plate, you may try to find the headlights. And once you find a couple of them or one of them, you can say this is a vehicle, right? Similar here. If you find the nose, then you can say this is the image of a face. Or if you, for example, find a door in this image, then you can say this is basically the image of a house. Okay, this is how you would solve the problem of classification. But how do you extract these features? So these are the features: nose, eye, mouth. This is the features for this problem. These are the features for this problem, and these are the features for this problem. So how can we extract these features? If we use a manual feature extraction method, then we need basically domain knowledge, we need to define our features, and then we need to detect these features for classification. But is it really possible, or is it really feasible to do this? You see, these are face images or statue images from different viewpoints. So viewpoint variation affects your features. Illumination conditions affect your features as well. These are, for example, the same penguins. You can't see even these penguins in this image. But with different illumination, things change. Scale always change things. These are two human beings carrying laptops. But since this guy is taller than this guy, it's difficult to say how we can use a manually handcrafted feature. Deformation always changes things. This is a cat, but it's a pretty deformed cat. Occlusions changes a lot. For example, this is still a cat, but only we have the head of the cat. The rest is occluded. The background clutter affects things. We have a cat here, but the background is too cluttered. And the intra-class variation affects a lot of things. All these things are chairs, right? But it's really difficult to select a visual feature that can define these chairs, because the only thing that makes these things chair is we can use these guys as chairs. So it's very difficult to manually define the features we would like to use for our problems. So that's why we use neural networks. The neural networks makes this problem a lot simpler for us. They try to extract the features automatically for our problems. So let's say we would like to solve face recognition or face detection problem. The neural network creates a couple of set of features, such as these low-level features, and then it combines these low-level features into mid-level features, and then it combines these mid-level features into more high-level features, and it solves the problem. And it doesn't ask you anything about which feature to use. Okay, it just uses the inputs you provide to the network and then try to estimate which feature is best for our problem. So that's basically how neural networks as well as the convolutional neural networks work. So which problems we can basically solve with convolutional neural networks? First of all, we can solve the problem of classification as well as localization. What do I mean with localization? Let's say you would like to find the sheeps on the image. Therefore, you need to draw a bounding box that's saying, okay, these are the sheeps I would like to find. This problem is called the localization problem. Okay? And classification problem is classifying these animals as sheeps. That's the classification problem. And the networks we will be seeing today will be mostly used for classification problem. So another problem, object detection problem. In this problem, in the object detection problem, you need to one by one say, this is one ship, this is another ship, this is another ship. Okay, you don't need the details of the boundary of the ship. Okay, you are just trying to find the ships. For example, you are not trying to find the grass, you are just trying to find the ships in the object detection problem, and you don't need the exact boundaries. So this is basically the object detection problem. We have another problem called semantic segmentation, where we can use the convolutional neural networks. In this problem, you are trying to segment the image in a way that all the things that function in the same way are segmented together. For example, this part of the image is grass, right? It functions in the same way. So this is segmented as grass. This part of the image functions in the same way. That's a road. So it's segmented as a road. And these are all shapes. You don't need the individual shapes. These are all shapes. So this part of the image is segmented as the shape. Okay. This is the segmentation, semantic segmentation problem. Okay. These definitions are important. So you need to understand the difference between classification, object detection, semantic segmentation, and there is one thing more, that's the instance segmentation. That's similar to semantic segmentation, but in semantic segmentation, we didn't care about the individual shapes, right? The aim was to classify these three animals as sheeps. But in the instance segmentation problem, you need to find each sheep. That's the basic difference between semantic segmentation and the instance segmentation. Okay, I hope now the convolutional neural network motivation is more clear. The problems we can solve with a CNN is more clear. We can basically solve classification, object detection, semantic segmentation, and instance segmentation problems. We can solve more problems with convolutional neural networks, but these are basically the most popular problems that we can use CNNs to deal. Okay, so learning visual features. In the previous lecture, we have seen we can basically feed stuff to the neural network and then we can do classification, right? And since an image is an m by m matrix, let's say n times m is p, why don't we just use p input values, feed this to a network, and then use this network? Maybe we can add a lot of hidden layers to this network and just use this network to classify the image. That's a solution, actually. You can do that. You can just convert this two-dimensional matrix to a one-dimensional vector. You can feed this to the network and then you can make classification or object detection. This is a valid solution. You can use a fully connected network, but if you do this, you will basically lose the spatial information. What do I mean that? If you had a two-dimensional array or two-dimensional matrix, the neighborhood information is kept there, right? For example, if you have one pixel here that's neighbor to another pixel, the relationship between this pixel and this pixel is lost if you convert this one-dimensional array into a two-dimensional array. Two-dimensional array into one-dimensional array. So we don't want that. We would like to preserve the spatial information. That's one thing. If we use this as an input to our neural network, that's too much parameters. And you need a very deep network in order to deal with this kind of problem. And training such a network is not that easy. So if we just convert a two-dimensional array into one-dimensional array, we lose the spatial information, then we have to feed a lot of parameters to the network. But instead of this, we can still use an image as a two-dimensional matrix, such as in this case. These are the pixels of the image. But instead of feeding this two-dimensional image, we can feed some parts of this image filtered by something. Okay, we can filter this image, we can create something else from this image, and we can feed this something else to the neural network. So this is what we will be doing in this class. We will see how we can convert this two-dimensional array, two-dimensional image, into a more dimensional tensor and feed this tensor to the neural network. And this operation of converting this two-dimensional image into this tensor is called convolution. So let's make the definition of convolution. In mathematics, in particular functional analysis, convolution is a mathematical operation on two functions, f and g, that produces a third function that expresses how the shape of the final function is going to be. Okay, that's basically how we can define the convolution. Let's try to make some examples. This is, for example, a convolution operation on function f, which is this guy, and function g, which is this guy. Okay. And if you convolve these two functions, for now let's assume that this is a magical operation. Okay. If you apply magic on these two functions, you come up with a function something like this, which is yet another function produced from these two functions, f and g. Okay. If you, for example, apply this magical operation on a different way, for example, g magical operation f, you come up with something like this. If you apply, for example, the same magical operation to f itself, you come up with something like this. So the idea is you have two functions, okay? You apply this operation, you come up with another function. That's basically how convolution works. So how do we use convolution for image processing? So this is an image, okay? An image is a function. That's a two-dimensional function. Okay, we said this is a two-dimensional array. Okay, and this function, which is called a kernel, that's called the convolution kernel. That's another function. And if you convolve these two functions, the image and the kernel, you come up with this. These are the edges of this image, right? So this basically function, if you convolve the image with this kernel function, you come up with the edges of this image. Okay. Similarly, if you apply a convolution between this image and this kernel function, okay, you again come up with the edges of this image. So the aim of the convolution operation in image processing is to create another image from the input image by using a convolution kernel. Okay, we will be using this term a lot because the concept we're working on is convolutional neural networks, basically. And it's always gonna be the same. We will have an image or a tensor, and we will apply convolution operation on this image or on that tensor. And you can think a tensor as a stack of images. Okay, so this is one image, right? If I had a lot of images stacked on together, that was going to be a tensor. And if I apply a convolution operation on that stack, I was going to obtain, for example, the edges of all the images on that stack. So what does the convolution operation does? You give an original image, you can use the convolution operation for edge detection, basically. You can use it for sharpening the image. You can use it to blur the image. You can use it for detecting the image or applying a lot of modifications to the image. So you just need to know, by applying a convolution operation to the image, you modify the image. You obtain something else. So you basically give the original image, you apply a convolution operation, then you come up with something else, which is different than the original image. Okay. Now let's try to understand what we basically do with the convolution operation. So that's basically a series of multiplications and summation. It's quite easy, actually. The name is fancy. Convolution is a fancy name, but the operation is pretty simple. We have the input matrix, which is this one. Okay. And we have the second function, which we call as the convolution kernel. Okay. We basically navigate this convolution kernel on top of the source image to obtain another image. And while we are navigating this kernel, we basically multiply all the elements of these two matrices and sum them up. Okay, that's basically the convolution operation. So let's try to make this as an example. We put our convolution kernel on top of this part of the image. Okay. Therefore, we need to convolve 4 by 0, because 4 and 0 are on top of each other. Here. 4 times 0. 0 times 0, because this 0 is on top of this one. 0 times 0, that's on top of this one as well. So 0 times this one, 0, which is the center of the kernel, times 1, which is the center of the projection of the kernel. 0 times 1, the projection of this one is here. 0 times 0, 0 times 1, minus 4 times 2. Okay, these are the multiplication operations. And at the end, we just sum these up. Okay, that's all 0, 0, 0, 0. We have just minus 8. So basically, for this convolution operation, for this part of the image convolved with this kernel, we have a result of minus 8. Okay, that's the new pixel value for the destination pixel. That's a very basic operation. That's a very simple operation. You just have multiplications and just the summation. So we have two operators. One is the convolution kernel. Okay. The other one is the input image. And at the end, we have an output image. So basically, we use this kernel for every pixel on the input image in order to come up with this image. So basically, we input an image with a kernel, we output another image. Okay, that's one thing you need to remember. We input an image, we come up with another changed image. So let's try to make another example. Here we will be convolving this 5 by 5 image with a 3 by 3 kernel. Okay, and the kernel is 101.0.1.0.1.0.1, as in this case. Okay, and each time you convolve, you basically move the kernel to either right or down. Okay, you convolve, you make another convolution, you make another convolution, you make another convolution. So basically, each time you convolve, you put a number here. Let me try to make this a little bit. So we applied the initial convolution. Let's make the initial convolution. So 1 times 1, that's 1. 0 times 1, 1 times 1. The summation is 2 here. 0 times 0, 1 times 1, it's 1. 0 times 1, 0. Up until now we have 3 in this convolution. Okay, 0, 0, and 1 comes from here. Okay, the summation is 4. Therefore, when we convolve this part of the image, the green thing is the image, the yellow thing is the kernel. When we convolve this part of the image with this kernel, which is 1, 0, 1, 0, 1, 0, 1, 1, 0, 1. Okay, this is the kernel. When we convolve this image with this kernel, we obtain a 4. So when we convolve this part of the image with the kernel, it's 1, 1, this is 1, it's 1 times 0, this is 0, 0 times 1, this is 0, 1 times 0, this is 0, 1 times 1, that's 1. For now we have 2, 1 times 0, it's 0, 0 times 1, 0, 1 times 0, it's 0, 1 times 1, it is 1, that's 1, 1, 1. Addition of this 3 is a 3. Okay, so it goes on like this. You basically multiply the elements together and then sum them up in order to obtain this convolved feature. One thing you should remember, you see this is a 5 by 5 matrix. Okay, the image is a 5 by 5 matrix. And our convolution kernel is a 3 by 3 matrix. And the output is not a 5 by 5 matrix, but a 3 by 3 matrix. Because when we put this here, and we started from here, we obtained 4. Then it shifted to the right, then we obtained 3. It's gonna shift to right one more time. You see, we have 4 here. Since this is a 3 by 3 convolution kernel, we cannot move this to right furthermore. Therefore, we have just 3 values here. And if we keep going, you see we want 1 cell down. Okay, therefore we have 3 cells here. So convolving a 5 by 5 matrix with a 3 by 3 matrix, we obtain a 3 by 3 matrix. We lost 1 row from here, 1 column from here, 1 row from here, and 1 column from here. Okay, so these guys are gone. You should remember this as well. So this is basically how convolution works. You just multiply these values and sum them up, and then output this as the new value, as the convolved feature. So let's try to make another example. That's something we can. So basically what we do is we convolve this with this. That's 7 times 1, you see here, plus 4 times 1, 4 times 1 here. That's 3 times 1 plus 2 times 0. Okay, 5 times 0, 3 times 0, 3 times minus 1, 3 times minus 1, 2 times minus 1, which is basically 6. Now we are done with this part of the image. We will be shifting our convolution kernel to here. Okay, so we have 2 times 1, 5 times 1, 3 times 1, and it goes on like this. Then we obtain a minus 9. And again here we have a 5 by 5 input image. We have a 3 by 3 convolution kernel, and the result is a 3 by 3 matrix. Okay, so it goes on like this. You shift either right or to down. And this shifting operation is called stride. That's a terminology you need to know. By defining the stride width, you can basically, for example, this is stride 1. The convolution kernel moves 1 pixel. If you define, for example, stride as 2, the convolution kernel moves 2 pixels to the right or to down. Okay, that's one thing you need to remember as well. So what we can do with the convolution operation, as we have seen, we have an input image, we have the convolution kernel. We can, for example, make edge detection such as this one or this one. We can do edge detection, sharpening, blurring, as well as other image enhancements with convolution operation. So how can we use convolution for convolutional neural networks? Let's try to remember. We said the image is a two-dimensional matrix, and in order to feed this two-dimensional matrix to a neural network, what we could do is we could convert this two-dimensional matrix into one-dimensional matrix and then feed all the pixels into neurons. But if we do this, we have seen that we cannot preserve the spatial information. We cannot make use of the information that a pixel is the neighbor of another pixel. And if you lose this information, for example, it's quite difficult to make edge detection, because edge detection relies on the fact that a pixel is neighbor of another pixel. Okay. So in order to preserve this, what we can do is, instead of converting this two-dimensional matrix into a one-dimensional matrix, we can use convolution on the input image to create convolution layers. Okay. So that's the idea behind convolutional neural networks. Just use the convolution operation on the input image to create convolution layers and feed these convolution layers to the neural network. So that's basically the convolution operation we have seen. You have the convolution kernel, you have the image. From that image, by moving the convolution kernel to right and down, you come up with a series of other images, which are called tensors. Okay. So we can use different sizes of filters. I will call them as filters from now on instead of kernels. And the idea is simple. You can learn the local features from these tensors. Okay. And in order to do that, we just need to make convolution, nothing else. So how does this work? Let's try to solve the problem of finding an x. Okay, this is an x, right? That's simple. All these bright things are, you can think this as an image, this is an x image. But how can you tell whether this is an X image or not? This is supposed to be an X image drawn by a not very talented person, right? But this is still an X image. Okay. Therefore, we need to find somehow features that defines this as an X image. So what if some filters could give me this part of the image, and this part of the image, and this part of the image? Then if I basically see this guy, and this guy on the image on the right side, then I could still tell this image is basically an X as well. Okay. So I just need an operation which tells me whether this image contains this kind of features. Okay. So what if I had filters like this? For example, if I had a filter which is 1, 1, 1 on the diagonal and minus 1, minus 1, minus 1 on the other parts of the filter, this filter could tell me because it's gonna give a high value when I convolve this filter with this part of the image, it's gonna produce a high value, right? Similarly, if I convolve this filter with this part of the image, that's gonna give a high value as well. Whereas if I convolve this filter with this part of the image, that's not gonna give a very high value. Basically, this filter will be used to detect these features, okay? And similarly, this filter can be used to detect this small x at the middle, and this feature can be used to detect this part of the x. And the whole idea behind convolutional neural networks is we just learn these filters, okay? So you are not given these filters. You are basically given the image, and then you try to learn these filters in the training phase. Once you learn these features in the training phase, during the prediction phase, you can just use these filters in order to find low level, mid level, and high level features on the image. Okay, that's basically the whole idea behind convolutional neural networks. Try to learn the filters that are relevant to your problem. You see, if you have a filter like this, then you come up with a high value here, because that's basically a convolution operation. Okay. So this is yet another example of convolution. We have done, I think, quite a few convolution operations, so I'm gonna skip this. So let's try to make this a little bit slower. We have seen the animation for this convolution operation. Let's try to make this a little bit slower. So this is our image. This is the convolution filter. This is a 5 by 5 image. This is a 3 by 3 convolution filter. Therefore, we will be coming up with a 3 by 3 feature map. Okay. We have 1, 0, 1, 0, 1, 0, 1, 0, 1. So this part of the image is 1, 1, 1, 0, 1, 1, 0, 0, 1. If you convolve this part of the image with this filter, we're gonna get a 4, because 1 times 1 is 1, 1 times 0 is 0, 1 times 1 is 1, that's 2 up until now, 0 times 0 is 0, 1 times 1 is 1, that's 3 up until now, 1 times 0, that's 0, 0 times 1, 0 times 0, 1 times 1, we had 3 here, we have 1 here, we have therefore 4. Okay. Then we basically move the filter, the convolution filter, to right, because we have stride 1. We are moving 1 pixel to the right or to down. Now we have 1 times 1, 1 times 0, 0 times 1, 1 times 0, 1 times 1, that makes 2. 1 times 0, 0 times 1, 1 times 0, 1 times 1. If you add them, you obtain a 3. You basically move your filter to the right. Once you cannot move further to the right, you go back to where you begin. You move 1 stride down. For example, if your stride is 1, then you move 1 pixel to down. If your stride is 2, then you move 2 pixels to down. So let's try to convolve this part of the image with the filter, just to understand in a better way. 1 times 1 is 1, 1 times 0 is 0, 1 times 1 is 1, that makes 2 up until now. 1 times 0 is 0, 1 times 1 is 1, that makes 3 up until now. 0 times 0 is 0, 1 times 1 is 1, that makes 4 up until now. 0 times 1 is 0, 0 times 1 is 0. That used to be 4, the summation of the convolution. And this value here is the result of the convolution of this filter and this part of the image. I hope it's clear now. So the general structure of a convolutional neural network. So this is what a convolutional neural network looks like. Okay, we have here the input image. This is one tensor. Okay, these are the convolution maps. These are the pooling layers. We will see what they mean. And these are the fully connected layers. Okay, we have basically three operations for the convolutional neural networks. The first operation is convolution, which is applying filters to generate feature maps. We have the second operation to create nonlinearity. We apply an activation function. We usually use ReLU, which we had seen in the previous lecture. And then we have another operation called pooling, which we will be using for downsampling the image or the tensors. Okay, that just makes three operations for creating a convolutional neural network. So input image, convolution layers, we have a downscaling operation, let's call this pooling, and then we have another layer. Just forget about these definitions for now. Just try to remember we have convolution, we have the activation function, and we have the pooling. So let's focus on the first operation, which is the convolution. We have seen what convolution means. In TensorFlow, in order to create a convolution layer, we use this term, TensorFlow.keras.layers conv2d. Okay, this is gonna create us a convolution layer. So we had seen basically how we can use the convolution operation. So I'm not gonna go into the details of this slide. Basically, what we will be coming up with this convolution operation is a tensor, which looks like something like this. Okay. Assume that we have an image 32 by 32, width 32, height 32, and that's one dimensional. That's a black and white or grayscale image. Okay. And basically, this convolution layer gives us this tensor in this cube, which has a certain width, a certain height, and a certain depth. Okay. And in order to define this layer in TensorFlow, we need to define three things. Okay. First, we need to define the number of filters, which means basically how many tensor we need here. That's the depth of this layer. Okay. If we say, for example, 32, that means we will have 32 two-dimensional arrays in this layer. Then we will be defining the kernel size. And this kernel size is basically the kernel that we will be using for the convolution operation. So this convolution operation will carry this layer, carry this one-dimensional layer into this d dimension by using the convolution operation. Okay, so for, let's say we have 32 layers here and we have one layer here. We will apply convolution operations, a series of convolution operations, in order to create these 32 layers from this one layer. And the optimization problem will be solving what operation we will be applying this filter in order to come up with these 32 filters. Okay. And the strides, we will come this later. Strides tells us basically how much our filter is going to move to the right or to the down. Okay, for now just forget about this. Just concentrate. We need number of filters here in this layer, and we need to define the dimensions of the kernel that we will be applying to the previous tensor in order to get this tensor. Okay. So once you define a conv2d layer in TensorFlow, you basically create another layer from the previous layer by applying convolution operations. That's why we had seen the convolution operation. So that's the operation the network uses in order to obtain this layer. Okay. Once you basically apply this, you need an activation function to create nonlinearity. Okay. And remember from the previous lecture what relay was doing? It was basically mapping all the non-zero minus values to 0, okay, and all the non-zero positive values to itself. So if you have a negative value, if you apply ReLU, rectified linear unit, if your value is, for example, -5, you map it to 0. If you have anything smaller than 0, then you will have 0. If you have anything larger than 0, you will have the same value with ReLU. So you apply the convolution, you apply the activation. Now we have the concept of pooling. An image is a very high dimensional data. It has a lot of pixels usually, and you don't want to deal with all the pixels. So you would like to refine your features as you go through the network. And in order to do that, you basically reduce the resolution of your features. And the operation we use for reducing the resolution of our features is the pooling. Okay. And the idea behind pooling is inside a region, you select one value and you create another feature map from these values. We usually use max pooling, which means we basically get the maximum value inside a given region. Okay. For example, we right now have a 4x4 matrix. Okay, this guy. If we apply max pooling to this 4x4 matrix with a pool size of 2x2, which means we will be using 2x2 areas inside this matrix with a stride of 2, which means we will be moving this 2x2 kernel to 2 pixels. Okay, and we will apply a max pooling, which means I will be choosing the maximum value from this region. For example, 6 is the maximum value in this region, right? So you put 6 here as the output value. Since our stride is 2, we move this filter 2 pixels right. We come up here. Okay. The maximum value in this region is 8. So we put this 8 to here. Our stride is 2. We cannot go right any further. We go back to our initial position. We go 2 pixels down. Okay. If we go 1 pixel down, we land here, right? If we move 2 pixels down, we land here. And the highest value in this region is 3. I put this 3 as the output value. And then I move our kernel 2 pixels to right. I land here. And the maximum value here is 4. I output this value as the 4. So what I did is I had a 4x4 matrix. I applied a max pooling operation with a 2x2 filter and stride 2, and I came up with a 2x2 matrix. So I basically downscaled this 4x4 image to a 2x2 image. So one thing you should remember about pooling is we would like to reduce the dimension of a filter. So this is a filter, this is a tensor. I would like to reduce the dimension of this tensor, and the stride basically decides how much I can reduce the dimension. If you take stride as 2, for example, I reduce the dimension into half of the filter. If this is a 4x4 matrix, then I end up with a 2x2 matrix. Okay, so these 3 operations we will be using in order to create our convolutional neural networks. And once we create a convolutional neural network, it's gonna learn low-level features, and then it's gonna combine these low-level features into mid-level features, and it's gonna combine these mid-level features into more higher level features. Okay, so this is what a convolutional neural network looks like. This is basically the input image. We have 3 layers here, right? You can just think this as one layer as well. If you have a colored image, then you have R, G, and B channels, which makes it 3 layers. That's why you will be usually seeing this as 3. For now, just for the sake of simplicity, assume that your image is a 2-dimensional matrix, one layer. And we will just be using not the RGB values, but we will be using the brightness values only. Okay, so the input of a CNN is an image. Then we have convolutional layer plus the activation ReLU. Okay, and then we have the pooling layer, which will be used to reduce the dimension of this convolution plus ReLU layer. And then from this pooled layer, we will have another convolution plus ReLU layer, and we will have another pooling layer, which is going to reduce the dimension of this tensor to this. Okay, and it keeps like this. This is the most basic convolutional neural network for classification. You can basically use this for classification problems. We will be using this for the example at the end of the lecture. But just for now, please remember we have the input image, we have convolution layer plus ReLU activation, we have the pooling layer, we have another convolution plus ReLU, we have another pooling layer. At the end of the network, we have other layers that we will be seeing. So what we have in this convolution layers plus ReLU is filters. Okay, we have seen this thing has a depth. We basically define the number of layers that we would like to have in this convolution layer. Okay, for example, if we say I would like to have a depth of 32, then we will be having 32 filters here. So this tensor will be composed of 32 layers. This is one layer, for example. This image is just one layer. If you choose to have 32 layers in this layer, then this tensor is going to have 32 layers. And for classification, at the end of the network, we need a special data structure where we basically have a dense network, fully connected, flat dense network, so that we can make the classification decision. We will be seeing how we can basically define this, but for now just concentrate on this part of the network. This is just the end of the network, which will be using the features coming from the left side of the network. So before we go into the details of the network, let's remember the very basic neuron definition from last week's lecture, where we wanted to solve the problem of converting Celsius to Fahrenheit. So we basically defined the network as a sequential network. That was the model definition. We basically added a layer, dense layer, which has one neuron with one input. Okay, we will be using something similar. That's not gonna be a dense layer, that's gonna be a convolution layer. Okay, That's going to be the basic difference between the convolutional neural networks and this very simple artificial neural network. In artificial neural networks, we use dense layers. In convolutional neural networks, we use convolution layers. Okay, but the definitions will be similar. And what we had done is, after defining the layers, where we had one layer and one basically neuron in this case, we basically defined the optimizer, which is the Adam optimizer in this case, and we basically defined the loss function, which is the mean squared error in this case. And once we basically define this, the model definition is ready. We defined the sequential model, we added the layer, we compiled it with optimizer and the loss function. And the rest is just training. So it's gonna be quite similar. But for convolutional neural networks, as I said, this layer definition will be a little bit more tricky. So this is the convolutional neural network we will be trying to create. So you see, we're gonna have convolution layer max pool, convolutional layer max pool, and then we will be flattening these layers. We will be adding two dense layers to our network. So here, these two lines of code is going to be used for defining this part of the network. So this says conv2d 32, which means we will have 32 filters in this tensor. Okay, the depth of this tensor is, in this direction, it's gonna be 32. If it was, for example, 64, it was going to be a bit thicker, such as this one. Okay, so we define the number of filters. We define the convolution filter size, which is going to be 3 by 3. Okay, and then we define the activation function as ReLU. So this line basically defines this tensor. Okay, and as we discussed, we would like to reduce the dimension of this tensor, so we will be applying max pooling. Okay, and this max pooling operation with pool size 2 and stride 2 will reduce the dimension of this tensor into this, which is half of this tensor. Okay, so this part of the network is just these two lines, right? And basically this part of the network is these two lines. As you see here, we have a thicker tensor than this one because we have 64 filters. Okay, we still have 3 by 3 convolution operators or kernels, and we will still be using ReLU as the activation function, and we need to reduce the dimension of this tensor as well. Therefore, we will be applying a max pooling operation here with pool size 2 and stride 2. So these two lines are basically responsible from this part of the network. And in order to make classification with this network, now we have actually refined all the features. We started with the image, we created 32 filters from this image, and then we refined these 32 filters by reducing their dimensions with max pooling, and then we applied another convolution operation to create 64 filters from this tensor, and then we reduce the dimension of this tensor with max pooling to this. Here we have refined or higher level features. Okay, now we need to basically feed these higher level features in a network structured like this. So you need to flatten these three-dimensional filters, and we do this with these 3 lines of code. You flatten basically this 3-dimensional filters, and then you create a dense layer with 1000 neurons with activation ReLU, and then you apply another dense layer with 10 neurons, which is going to make the final classification decision. In this case, we have 10 classes, therefore we have 10 neurons at the very end of the network. Okay, you could add more dense layers to here, doesn't matter, but usually just after flattening you can add one dense layer and then you can add the final dense layer. And as the activation, as you see, we didn't use ReLU, we used softmax, since this is a classification problem. Okay, so that's how we basically define our convolutional neural network. So this was basically the most simple architecture for a convolutional neural network. And let's see what problems we can solve this with this kind of architecture. So this was the architecture. This is basically the convolution layer. This was the pooling layer. This is another convolution layer. This was the pooling layer. And then we had dense layers after flattening. Okay. With this kind of architecture, we can solve classification problem. What I mean with classification problem is, we are given an image, we say whether this is a taxi or not, or we say this is a taxi, or this is a human, or this is an animal. Okay, this was the classification problem. But in order to make things a little bit more complicated, assume that we are given an image with a background. You see, we don't just have a taxi, but we have other stuff as well with the taxi. For example, we have pedestrians, we have other taxis as well. So we would like to find the location of the taxi, which was the object detection problem, if you remember. So how we can do that, basically? We can do this with different architectures. So the problem we would like to solve right now is, we would like to find the location of the taxi, we would like to find the location of the person and the truck. Okay. So what we can do is, we can basically get some patches from the image. Okay. We can get random patches with random dimension. So we can get a patch like this. If we get a patch like this and try to classify it, that's gonna give us a taxi. But if you get a patch from here, it's not going to give you a taxi. That's gonna be classified as unknown, for example. Or if you get a patch from here, that's going to be classified as something else. If you get a patch from here, it's going to be classified as a pedestrian. This is one way to do the stuff. You can still use the architecture we have seen up until now. You can get random patches. This is called a moving window solution. If you move the window, for example, if you select the window from here, you move it to the right by changing its scale. At some point, you can come up with a taxi. At some point, you can come up with a pedestrian. But you need to check a lot of scales, a lot of positions, a lot of sizes, and that takes a lot of time. So what if we had another network which could extract regions and proposes them as potential objects? And what if we could just concentrate on these regions? So this is another architecture, another convolutional neural network called RCNN. Okay. And as you study further for the convolutional neural networks or artificial neural networks, you will see a lot of different architectures. And CNN is a popular architecture, RCNN is a popular architecture as well. And we have other architectures like faster RCNN, where the aim is, you are given an image, you basically apply some convolutional layers, and then it proposes you some regions, and out of these regions you apply other operations, and then you come up with detections. Okay, this is faster RCNN, for example. And this is yet another very popular network called UNet, where the aim is to make segmentation, semantic segmentation. Remember, cows are segmented as animals. This is segmented as grass. This is segmented as forest. This is segmented as sky. So the basic idea is similar, but as you see, the architecture of the network is different. An image is given, the dimension of the image is reduced by convolution operations as well as pooling operations, and at some point here, at the middle of the network, we basically start to increase the dimension of the image or the dimension of the filters. That's why it's called UNet. And the operation we use in order to increase the dimension of the filter is conv2d transpose. And this is the transpose or inverse of convolution operation. With the convolution operation, if you remember, we were reducing the dimension of the filter. With the transpose of convolution 2D operation, we basically increase the dimension of the filters. I don't expect you to understand these architectures at the beginning. Just try to understand there are basically different architectures for different problems. For today's lecture, we basically concentrated on this architecture where we have an image, convolution layer max pooling, and then flattening and dense layers. This is a very classical network for classification problem, but for more complex problems such as object detection or semantic segmentation, we usually use more complex architectures such as RCNN or such as UNet. So for this lecture's example, we will be using the fashion database. Let me introduce the database. We have very small images of clothes basically. Here you have trousers, Pradas, and other stuff. We have different classes of fashion objects, and we will use convolutional neural networks in order to classify these images. I will be providing basically the data, but you can get the data and the source code from Kaggle as well. We have different classes. We have, for example, Pradas, we have t-shirts, we have shorts, we have dresses, and some other clothes, even I don't know what they are. And the basic problem we are trying to solve is we will be given some input images. We will first train a classifier. We will have 70,000 images, 70,000 very small images. And we will be using 60,000 of these images for training and 10,000 of these images for testing. It's similar to the MNIST database. If you remember, we had 28 by 28 grayscale images in MNIST database as well. Here, for this fashion database, we still have 28 by 28 grayscale images, which represent, for example, shoes, trousers, bags, and other stuff. We have basically 10 classes. Okay, we have t-shirt, trousers, pullover, dress, coat, sandal, shirt, sneaker, bag, ankle boot, and these are the classes we are interested in. So given an input image, it's going to give a probability out of these 10 classes. Okay, for example, for this input image, if we can train our classifier in a good way, we will expect the classifier to give the highest probability to sneaker. So it's gonna give 10 probabilities because we have 10 neurons at the end of the network. Okay, but the highest probability is going to be for the sneaker. And if we give this ankle boot, for example, the highest probability will be here. If we give bag, the highest probability for this image will be for bag, And if we give t-shirt, the highest probability will be for t-shirt. Okay. And these are basically the images, 28 by 28 two-dimensional data. 0 represents black, 255 represents white, and each image is represented by 700 pixel values. That's a one-dimensional data. We will be converting this into two-dimensional 28 by 28 two-dimensional metrics in order to process for convolutional layers. So let's go back to Google Colab. I think I need to reconnect for. So before we start our example, let's recap the mathematics behind this. Let me see. So it's gonna be given an image, we will apply some convolution, we will create some convolution kernels, and at the very end, after convolution layers, we will have a dense layer which is going to output either of these classes. Okay, let's see whether Google Colab is ready. Seems our drive is not ready yet. I'm waiting for my drive to be installed. Okay, now it's installed. So as usual, we will be importing our Python libraries. Different from our Anaconda experience, we have TensorFlow in Google Colab, which is pre-installed in our environment. We will be using two CSV files. One is containing the training data, one is containing the test data. I will be providing this data. So if once we load the data, we will check the size of the data. That's a little bit big, so it takes a little bit time for loading. When you take a look at the shape of the training data, as I said, that's 60,000 images, and each image is composed of 785 pixels. So this, for now, it's a one-dimensional array. Okay, if you check the test data, that's 10,000 images with same dimension. Both two are just one-dimensional arrays for now. And if you take a look at what we have with the training and test data by using the pandas head, you see we have 5 rows because we used head. We have 785 columns. Now this part is a little bit tricky. The first column is label. Okay, that's basically the class that we would like to solve. Okay, that's the class of that image, and the rest is the pixels. So it starts from pixel 1 and it goes on like this. Okay, the rest is pixels. 28 by 28. We have 784 pixels. But we will be using the first column as the label of the image. 2 means, for example, shoe. 9 means it's gonna be ankle boot or something like that. Okay. So we first need to convert our data into NumPy array so that we can use them. You see, these are not floating point numbers. If you want to use something with artificial neural networks, please remember artificial neural networks gets real values like float or double, and they give you float or double values. You cannot use integers, or you shall not use integers unless otherwise stated. So we convert our data to floating points. Now let's try to display what we have inside our training data. For example, let's try to display this one, 101st image in our dataset. So this looks like an ankle boot or Prada or something like this. Okay, let's for example display 111. See, that's a sneaker. Let's try to display 115. That's a sneaker as well. So we will convert this one-dimensional data. That's why we use reshape to 28 by 28. We need to convert this one-dimensional matrix to a two-dimensional matrix in order to use it for our convolutional neural networks. So one thing before we do training, we need to divide all the brightness values to 255 so that everything is between 0 and 1. Okay. Remember, the brightness values were ranging from 0 to 255. We don't want that. We would like to have real values that are between 0 and 1 for training. Okay. So that's why we need to divide both the training and the testing to 255. So this expression here says I would like to use from first column to the rest for the X train, because we have label in the first column. So that's why we have this expression. We put Y train, training for the first column, and from the second column to the last column we use as an image, and we divide into 255 so that we have an image which ranges from 0 to 1. The brightness values ranges from 0 to 1. Okay. Let's do this. Let's do the same for the testing as well. Now we have our training and testing data in one dimension. Just to check, X train shape, we have 60,000 images, but they are still one-dimensional matrices which are not suitable for convolution operations. So we need to reshape them, and this is how we reshape them. We know that the images are 28 by 28 pixels. So we need to create a tensor, okay, a tensor that's 28 by 28 by 1. Don't forget this one. This is important. We are creating a tensor. So we need 3 dimensions. That's width, that's height, that's depth. And since this is a brightness value image, this is a grayscale image, that's depth is 1. Okay. And if you check the shape of the X train now, what you will come up with is 60,000 images, 28 by 28 by 1. So this is the dimension of our tensor. All right. Okay, now comes the interesting part. We will be defining our network. So we need to import some stuff from Tensorflow. Once we import them, that's the similar command from last week. We will be creating a sequential model, and we will be assigning it to CNN. Okay. Then we will start adding our layers. So the first layer is we will be using the CNN architecture. So we will be using a convolution layer which is going to have 32 filters, and we will have a 3 by 3 convolution filter in order to create these 32 filters. And as activation, we will be using ReLU. And since this is the first layer of our network, as we did last week, we need to define the input shape. The thing is, you don't need to define the input shape for the rest of the network. You can define it, but you don't need to. But for the first layer of your network, you always need to define the input shape. And in this case, we will be providing images that are 28 by 28 by 1, since we have just brightness values. If that was a colored image, if it was an RGB image, we were going to, for example, provide 28 by 28 by 3. Okay, we were going to provide a tensor with depth 3. Right now we are providing a tensor with depth 1. So this part is important. You need to assign the input shape. You need to assign the activation function. You need to define how many filters this convolution layer will have. And you need to define the size of your convolution kernels. Okay. And if you remember from the CNN architecture, let's go back to our CNN architecture. Right now we defined this, okay, with 32 filters. Now we need to reduce the dimension of this layer into half by applying the pooling operation, okay? And this is how we do it. You basically define a max pooling layer, and then you reduce the dimension of your layer, okay, your tensor. Now we did this. We are here. We will be defining another convolution layer, okay? And we will be having 64 filters for this layer, okay? And this is why we have 64 here. And we will be using again a 3x3 convolution kernel. We will be using ReLU as activation function. And with this line, we basically defined this layer, okay? From these layers, after max pooling, we defined another convolutional layer, which is this one with 64 filters. And we need to reduce its dimension. Therefore, we define another max pooling layer, which is this little guy here. Now we can define another convolution layer here. Doesn't matter. We can remove this. We can have this as well. So this is yet another convolution layer with 64 filters. We're not gonna apply max pooling. You can put a max pooling here as well. You can give it a try to see how that's gonna change your results. After this operation, we are basically done with creating the convolution layers, okay? And since that's gonna be a classification problem, we have the refined features here. We need to use these features in order to make the classification decision. So first thing we will be doing is we will convert the tensor, three-dimensional tensor here, into two-dimensional tensor, so that we will have a classification decision making layer here. So the first thing we need to do is we create a flattened layer, and then we put a dense layer with 64 neurons with an activation function of ReLU, okay? And then we put a dense layer with 10 neurons, since we have 10 classes. This is the last layer. Therefore, we have the activation of softmax, okay? Very basic, very simple. Create a convolution layer with 32 filters with activation ReLU. Create a max pooling layer. Create another convolution layer with 64 filters. Create another max pooling layer. Create another convolution layer with 64 filters. That's just to make things a little bit more complicated. You could just remove this line, basically. Let's execute. And at this point of the definition of our model, we are finished with the convolution layers. So we will be using the convolution layers in order to make a classification prediction. Therefore, we put a flattening layer to convert this three-dimensional data to two-dimensional data. And then we put a dense layer with 64 neurons. And then we put the last layer with 10 neurons, since we have 10 classes. Okay, so remember this summary command. from last week that's basically giving us the shape of our network. Let's try to analyze it. Okay. So our input shape is basically 28 by 28, right? The first convolution layer is 26 by 26 because we have a 3 by 3 convolution kernel. Remember from our convolution example, the convolution was causing a little bit decrease of width and height. Okay, and you see the depth is 32 as we defined here. So we have this many parameters which are weights and biases. Okay, and then we have a max pooling layer. You see it used to be 26 by 26 filters. Right now we have 13 by 13, which is half of these numbers, because that was the aim of max pooling, right? We were trying to basically reduce the dimension of our filters. The dimension of our filters was 26 by 26. Now we have 13 by 13, and the number of filters, or the basically depth, is same. Okay, with the second convolution layer, we have these dimensions, and we said I would like to have 64 filters. Right now in this layer, you see, I have 64 filters with 11 by 11 layers. Okay, and once I apply a max pooling, I get half of these numbers because I'm trying to reduce the spatial resolution basically with max pooling operation. So I keep the number of filters basically, and I reduce 11 by 11 to 5 by 5. Okay, and since I have another filter here, which is yet another convolution layer with 64 filters, I have this in my network. Okay, up until now I'm here and here in my network summary. Now I have a flattening layer. You see, you have the flattening layer. You have a dense layer here, as you see, and you have yet another dense layer with output shape 10. And if you add up the number of parameters, you see we have quite a few parameters to tune. So this was basically the definition of the neural network, how we could define the network. I'm not gonna train the model. I leave this as an exercise. I will just load the model that I trained. The training takes like 2 hours if you would like to train it by yourself. So if you train it, you will need to use this code. Okay, first you need to compile the code by defining the loss function. Here we will be using sparse categorical cross entropy, and then you need to define the optimizer. Once you make these definitions, you need to define the number of epochs, and then you will be using the X-train and Y-train values with fit commands. Here you need to define the number of epochs, and we have another concept called batch size. This is important, guys. The batch size means in each epoch you don't use all the data. Remember, we have 60,000 images for training, and batch size says just take 512 of these images and use these batches for the epochs. Okay, so that you don't memorize, you don't overfit to the network. And if you run these 2 commands by yourself, what you will be observing is we have losses here. Okay, I need to show this. You see the loss is decreasing with every epoch. This is the first epoch. You see the loss is quite big. The accuracy is kind of okay. And you see loss is decreasing, and that keeps decreasing. There might be some fluctuations, but you see the loss is still decreasing. We are at the epoch 43. There are a lot of epochs. You see the loss is decreasing, accuracy is increasing. So that's a good model. That's a simple problem. These are very small images. That's a very simple problem. And that's a pretty good network for this kind of very small problem. You see, even at the epoch 90 or 96, we have an accuracy pretty close to 1, and we have accuracy 1. We are basically overfitting after this point. So if you try it yourself, for example, reduce the number of epochs. You can play with that. But remember, it takes time. So let's load our model that I trained beforehand. If you basically compile and fit, if you train this network, you can basically use this command, cnn.save, to save your model, and you can reuse this model afterwards. Okay. You need to remember this as well, because training an artificial neural network, and especially if this is a convolutional neural network, that takes time. That really takes time. Even for this very small problem where we have 60,000 images for training, and they're pretty small images, that took 2 hours in Google Colab. In a proper computer, that would take minutes, but in Colab it took 2 hours. But if you don't want to lose your model that you created after 2 hours, just use this command. Save your model. Okay. And in order to evaluate your model, you can just say CNN evaluate. We have the X test, Y test. So we have quite good accuracy. And if you would like to make an individual prediction, for example, from the X test, let's try to make the prediction for the first value, or let's try to make the prediction for the 10th value. So model.predict. You need to use it like this. You need to convert this to a NumPy array in order to make the prediction. That's important. And you see, we have 10 numbers here, 10 probabilities. And 1, 2, 3, 4th is basically the highest probability, which means it's almost certain that this is from class 4. Okay. And let's see what we have in class 4. That's address. And if we go back to our slides, I think that's correct. You see, yes, that's address. 1, 2, 3, 4. So that's address. So our network gave 10 numbers because we have 10 classes. Remember, we have 10 neurons at the very last part of our network. So it gave us 10 probabilities, but the highest probability, which is the 4th one in this case, says this is the given test image, the 10th image is basically address. Okay. I provided you a couple of functions that you can check basically the result of your network. It's basically giving you the prediction class and the true class. You can modify the network. You can use this function in order to have a visual understanding of the success of your network. Please try to modify this network. Try to understand the architecture of the network. We added, for example, another convolutional layer. You can just remove this layer. You can add another max pooling layer, for example, in order to reduce the dimension a little bit more. You can change the number of filters. If you reduce the number of filters, the training takes less time. If you increase the number of filters, the training is gonna take more time. Please try to modify the network. Please try to understand the architecture of the network. This is the simplest architecture for convolutional neural networks. If, for example, you would like to solve segmentation problem, you will need to create much more complicated architectures. So if you understand this, you will understand almost all the network architectures. And please try to remember, we basically use different architectures for different problems. So let's try to summarize this week's content. We can use deep learning for computer vision, and if you want to do that, we basically use convolutional neural networks. We have the convolution operation. We have special layers called convolution layers. We basically have basic architectures for different problems. We can solve classification problem as well as segmentation problem, object detection problem with convolutional neural networks. And usually the network architecture changes from problem to problem. Okay, that was it for convolutional neural networks. I hope that was useful.